Our project topic is home automation using Arduino, Picsimlab and Blynk IoT app. This project demonstrates how common home systems like lighting, temperature control and water management can be automated using affordable hardware and IoT connectivity. Automation is becoming an integral part of modern living. In this project, we simulated a smart home setup where garden lights, heaters, coolers, and a water tank are controlled automatically or remotely through the internet. The entire system runs virtually using Picsimlab and is connected to the Blynk IoT app for real time monitoring. The C programming fundamentals. The Arduino environment uses simplified C programming. It's essential to understand C fundamentals like data types, constants, variables, and control statements, since all hardware logic is implemented using these basics. The C character sets and identifiers. C uses letters from A to Z in both uppercase and lowercase, digits from 0 to 9, special characters and white spaces to form the basic elements of program such as variables, constants and expressions. The white spaces used in C program are blank space, horizontal tab, carriage return or a new line. Identifiers in C are names given to program elements like variables, functions and arrays. They can include letters, digits and underscores but must begin with a letter. Since C is case sensitive, uppercase and lowercase letters are treated differently. Identifiers can be of any length, but keywords are reserved words with predefined meaning that cannot be used as an identifier. The keywords are reserved words that have standard predefined meaning. These keywords can only be used for their intended purpose. They cannot be used as a programmer defined identifiers. Example of some keywords are int, main and void. Data types. The data values passed in a program may be of different data types. Each of these data types are represented differently within the computer's memory and have different memory requirements. These data types can be augmented by the use of data types qualifiers modifiers. The data types supported in C described as below. Int, which is used to store an integer quantity. The character, it stores a single character of data belonging to the C character set. The float, it is used to store real numbers with a single precision. And double and void. The steps in learning C language is just similar to the steps in learning an English language. It includes alphabets, then we form the words, then the words form sentences, and a group of sentences is known as paragraph. Just like that, in C programming, the C language consists of alphabets, digits, and special symbols, which forms constants, variables, and keywords. And we give some instruction to the computer and we form the program. Introduction to embedded system. An embedded system is a hardware software integration combination designed to perform a specific function within a larger system. An embedded system is a computer designed for specific tasks such as washing machine or a fire alarm. Our Arduino setup acts as an embedded controller that performs automation tasks continuously. The characteristics of an embedded system includes is that they have a task. They are task specific. Typically consists of hardware, software, and firmware. Can be embedded into a larger system to perform a specific function, as they are built for specialized tasks within the system, not various tasks. They can be either microprocessor based or microcontroller based. Both are integrated circuits that given the system computer power. The structure of the embedded systems vary in complexity but generally consists of three main elements. Hardware. The hardware of the embedded system is based around microprocessors and microcontrollers. Microprocessors are very similar to microcontrollers and typically referred to as CPU or central processing unit, that is integrated with other basic computing components such as memory chips and DSPs. Microcontrollers have those components built into one chip, software and firmware. Software for embedded systems can vary in complexity. However, industrial grade microcontrollers and embedded IoT systems usually run very simple software that requires little memory. This is the general structure of an embedded system. It consists of sensor, analog to digital converter, MCU, digital to analog converter, and actuator. The embedded system classified as real-time embedded system, hard real-time, soft real-time, mobile embedded system, networked embedded system, standalone embedded system. The real-time embedded system are those systems that work within strict time constraints and provide a worst-case time estimation for the critical solutions. Hard real-time embedded system. This type of systems make sure that all critical processes are completed within the given time frame. This means that all the delays in the system are strictly time bound. Also, there is little to no secondary memory and data is stored in short-term memory. Soft real-time embedded systems are much less constructive than the hard real-time systems, but with the basic of the premise is same. Mobile embedded systems are small size systems that are designed to be portable. Network embedded systems are connected to a network to provide output to other systems. Standalone embedded systems are not reliant on a host system. The main requirements, it consists of a microprocessor and microcontroller. Microprocessor is a computer processor where the data processing logic and control is included on a single integrated circuit or small number of integrated circuits. Microcontroller is embedded inside of a system to control a singular function in a device. The memory In the memory there are two types of memory, RAM and ROM. The RAM consists of SRAM, which is static RAM, and DRAM, which is dynamic RAM. Internet of Things describes the network of physical objects or things that are embedded within the sensors, software, and other technologies for the purpose of connecting, exchanging data with other devices and systems over the internet. This is the IoT 7-layer architecture. The first layer includes physical devices and controllers. Then, second is connectivity. Third, edge computing. Fourth, data accumulation. Fifth, data abstraction. Sixth, application. And the last level is known as collaboration and processes. The project requirements are microcontroller at Mega 32P, an Arduino Uno board. Coding requires Arduino IDE, Internet, and then Blynk IoT app simulation deployed using Picsimlab, virtual serial port for serial communication, garden lights, LDR sensor, temperature system, LM35 sensor, water tank. It is serial communication protocol. Our project solution is control garden lights on basis of sunlight intensity. Lesser the sunlight, brighter the garden lights. Temperature system control, switch heater and cooler on or off remotely. Switch heater off automatically if the temperature indoor exceeds 35 degrees Celsius. Water tank control, switch inlet and outlet valve on or off remotely. Switch inlet valve off automatically if volume of the tank drops below 2000 liter. The garden lights, ADC light dependent resistor used to sense sunlight and send analog signals to microcontroller. It adjusts brightness of the garden light with respect to analog signals sent. The ADC has three steps: sampling, which is breaking continuous signals into discrete signals; quantization, discreting y-axis; encoding, assign digital value to each signal level resolution of the ADC. The temperature system. LM35 is an integrated analog temperature sensor whose electrical output is proportional to the degree centigrade. LM35 sensor does not require any external calibration or trimming to provide typical accuracies. Controlling heater and cooler remotely. Blynk mobile IoT app is used to remotely for controlling the heater and cooler. Arduino Uno is connected to the internet. Fireware configuration provided by the Blynk is used to connect data to the Blynk cloud. The water tank. Serial remote tank simulator is used for the water tank simulator. Virtual serial port used to set up serial communication between the Picsimlab and the serial tank. Conclusion: using Blynk IoT app and Picsimlab simulator simulated home automation where LED temperature system, serial tank resembles light, heater, cooler, and water tank in real time. CLCD acts like a dashboard used for displaying the events. Widgets from Blynk IoT app like button widgets are used to control heater, cooler, and inlet valve, outlet valve. Gauge widgets to display temperature and volume of the water. Thank you. As I have explained the working of this project, now my friend Neha will be explaining the actual working of how the project is built. Thank you.
Neha K from Siddhaganga Institute of Technology. So I'm presenting the working of IoT based home automation system. So this is the CLCD where the temperature is getting displayed. You are seeing that temperature and the volume is displaying on the CLCD. In our project, the first automation is garden light controlling. So it can be controlled based on the availability of the light. So here you can see a LDR sensor. This is having a slider. When we pull up the slider, you can see a LED is on. When we pull down the slider, the LED will get off. So it means that when there is a less light, the LED will be on. When there is more abundant light, the LED will get off. This is about the gardening of light. The next automation of our project is temperature control system using LM35 temperature system. Here you can see temperature is displayed on the CLCD. So the temperature can be controlled using a mobile application called Blynk. So this is the mobile application called Blynk IoT application. Here you can see a Blynk IoT application. There are two tabs. The first tab, they are having two buttons, heater and the cooler, and the temperature gauge to display the temperature. So here when we turn on the heater, it starts increasing the temperature. If the temperature reaches more than 35 degree, it automatically turns off and also display a notification the temperature is above 35 degrees Celsius. Turning off the heater and it starts reducing its temperature. When we turn on the cooler, you can see that the fan is rotating and the temperature decreases. When we turn off the cooler, the temperature is reduced and it will display on the CLCD. So this is about temperature controlling system. Temperature is reduced and it will display on the CLCD. So this is about temperature controlling system. So our next automation in our project is water tank, controlling the water tank through inlet and outlet valve. So there are two buttons for controlling the inlet and outlet valve and the gauge to display the volume of the water. Here you are seeing a serial remote tank. When we turn on the inlet valve, the water inflows, and when it get full, it will display notification that water level is full and water inflow is disabled. And then when we turn on the outlet valve, the water will move outside of the tank. We also automated that when water level is less than 2000, the water inflow enabled. It should stop when it reaches less than 2000. So when the inlet valve will on again, it will stop and push the notification that you will see that notification there that the water level is less than 2000 and the water flow is enabled. When the outlet valve we start filling the water, you can see the capacity of the water and it is all. In conclusion, our project successfully demonstrates a complete IoT based home automation system developing using Picsimlab for simulation and Blynk IoT application for wireless control. The main objective was to enhance convenience, improve safety, and optimize energy and resource usage inside a home. We automated three objectives here. The essential areas are the garden lighting, temperature control, and water tank management. For garden lights, we used LDR sensor to continuously sense the surrounding light's intensity and adjust the brightness of the LED. Accordingly, ensuring lights remain bright when there is a low sunlight and dim or turned off during daytime, which directly contributes to energy conversion. For our temperature control subsystem, we used an LM35 sensor to monitor real-time temperature values displayed on both CLCD and Blink gauge widget to manage home environment effectively. Users can remotely operate the heater and the cooler using blink buttons from anywhere in the world. Additionally, a smart threshold mechanism ensures safety and energy efficiency. If the temperature crosses 35 degrees Celsius, the heater automatically switches off and clear notification is displayed both on virtual terminal and CLCD, preventing overheating and saving power. The third subsystem focuses on water management. Using serial tank module, we monitor the water level inside the tank and control the inlet and outlet valves. The valves are shown on CLCD and blink and through the app. User can decide when to allow water inflow or outflow. To prevent water wastage and overflow, an intelligent automation feature has been implemented. When the tank is full, the inlet valve will automatically stop and notify the user, and similarly when the water level drops below the minimum threshold like 2000 liter, the system automatically enables the inlet valve to refill the tank. Through this project we are able to understand, practically apply key IoT concepts like cloud based monitoring, wireless communication, sensor interfacing, serial communication, dashboard visualization. We also realize how automation reduces manual effort and improves sustainability in real time home environment. Even though this setup is currently a simulation, it can easily scale and deployed using real sensors and hardware. Therefore, our project proves that IoT based automation is not only technically possible but also highly beneficial for modern households, making them smarter, safer, and more efficient. Thank you.